Hello everyone and welcome back. Next topic of this video session is resource allocation graph and deadlock handling methods of course operating system in Deadlock chapter. First I will start with resource allocation graph. Deadlocks can be described more precisely in terms of a directed graph called a system resource allocation graph. This type of graphs consists of a set of vertices and set of edges. So we can also say that a graph has two components like vertices and edges. Now vertices are of two types. One is process type, another one is resource type. Where process P is equal to P1, P2 up till Pn, the set consisting of all active processes in the system, and resource R is equal to R1, R2 Rn is the set consisting of all resource type in the system. Now in this graph, we will also consider two types of edges. That is request edge and allocation edge, that is also called assignment edge. A directed edge from process Pi to resource type Rj is denoted like this, which signifies that a process Pi has request an instance of resource type Rj and is currently waiting for that resource. The resource has not been received yet by the process. That's why this edge is said request edge. And a directed edge from resource type Rj to process Pi is denoted like this, and it signifies that an instance of resource type Rj has been allocated to process Pi, which is called an assignment edge. Pictorially, we represent each process as a circle and each resource type as a rectangle, and any resource type have more than one instances. We represent each such instances as a dot within the rectangle. Remember that a request edge points only to the rectangular box, but an assignment edge must also designate one of the dots in the rectangle. Now we will see an example of a resource allocation graph. Here we can see the sets of process, resources and edges, where we have three process type vertices, that is P1, P2 and P3, and four resource type vertices, that is R1, R2, R3 and R4. Here resource type R1 has one instance, resource type R2 has two instances, resource type R3 has one instance, and resource type R4 has three instances. Here in this figure, we can see that process P1 holding one instance of R2 and waiting for one instance of R1, and process P2 holding one instance of R1 and one instance of R2 and waiting for an instance of R3. Process P3 is holding an instance of R3, and in this graph we can clearly see that there is no cycle, so we can say that there is no deadlock. So from the definition of the resource allocation graph, it can be shown that if the graph contains no cycle, then no process in the system is deadlocked. If the graph does contain a cycle, then a deadlock may exist. Under this point, if graph contains a cycle, we need to consider 2 points of view, that is, number one is if resource type has exactly one instance, then a cycle in a graph implies that deadlock has occurred. And number two is, and if resource type has several instances, then there is a possibility of deadlock. So we can say a cycle in the graph is both a necessary and sufficient condition for the existence of deadlock if resource type contains single instance. But if resource type has several instances, then a cycle does not necessarily imply that a deadlock has occurred. In this type of case, a cycle in the graph is necessary but not a sufficient condition for the existence of deadlock. Here in this slide, we can see an example of a resource allocation graph with a deadlock. To illustrate that concept of deadlock, we can consider here in the same previous graph that where the process P3 requests an instance of resource type R2. Here we can see no instances of resource R2 is currently available. Here a request age is added from P3 to resource R2 in the graph. At this point, two minimal cycle occurs. Here in the picture, we can see the cycle. The first cycle is P1, R1, P2, R3, P3, R2 and in between P1. And the second cycle is P2, R3, P3, R2 and P2. So, in this situation, we can say process P1, P2, P3 are in deadlock situation because process P3 is waiting for either process P1 or process P2 to release resource R2. Process P2 is waiting for the resource R3 which is held by process P3. In addition, process P1 is waiting for process P2 to release resource R1. Now we will consider an example of a resource allocation graph with a cycle where there is no deadlock. Here we can see that a cycle exists here in this figure in between P1, R1, P3, R2 and P1. But we can observe that if process P4 may release the instance of resource type R2, then the resource can be allocated to P3, which breaks the cycle. And similarly, if the process P2 may release the one instance of R1 after finishing its task, then the resource can be allocated to P1, which also breaks the cycle. So the summary is, after studying all the examples of resource allocation graph are, if there is no cycle present in a resource allocation graph, then the system is not in a deadlock state. If there is a cycle, then the system may or may not be a deadlock state. Remember, this observation is very important when we deal with the deadlock problem. Let's start deadlock handling methods. We already discussed what deadlock is and what are the 4 conditions for deadlock to occur. Now we discuss how we are going to handle deadlock. Here we have 4 approaches to deal with the deadlock, and those are deadlock prevention, deadlock avoidance, deadlock detection and recovery, and ignorance. Before discussing broadly about how operating system handles deadlock in a computer system using these approaches, I want to share some real-life examples which will help you to understand the concept much more clearly. In our real life also, we use this type of approaches to solve problems. So first one is deadlock prevention. Prevention gives you a guarantee that no problems will occur in the system. Or we will say we can use a protocol to prevent deadlocks, ensuring that the system will never enter into a deadlock state. Means designing such a system which violates at least one of 4 necessary conditions of deadlock. The second one is deadlock avoidance, which is a lazier approach than prevention. It means it avoids the problem for the time being, though it will resolve the problem later. Or we can say it does not put any such restriction on the way the process requests for the resources, but system will decide whether the request will be immediately granted or the process have to wait for the release of other process that hold it. Means the system maintain a set of data structure, and using this data structure, which it takes a decision on runtime whether to entertain a new request or not. The third one is deadlock detection and recovery. It waits for the problem to arise and handles or deals with it from that time. Or we can say we can allow the system to enter a deadlock state, detect it and recovers. And the fourth one is ignoring the deadlock. Here in this approach, we can ignore the problem altogether and pretend that deadlocks never occur in the system. Means we ignore the problem as if it does not exist. This solution is the one used. This solution is the one used by most operating systems, including Linux and Windows. It's then up to the application developer to write programs that handles deadlocks. Next, we have to understand that which of these approaches are to be used on which problems. All of them are good as it is, and it depends how much effort, time or cost you want to invest on your solution, and also the nature of the problem matters here. Let's try to understand this point with an example. Suppose in spring 2019 semester, there are some students in CSE 321 course, and in a class there are different types of students, and each of them follows different types of approaches to complete the course. Some students follow the prevention approach, that means they study throughout the semester and follows a strict routine. To them, failure isn't an option. Getting the highest mark is their main goal or concern. Whereas some students in the same class follows the avoidance approach. That means they do not follow a strict routine throughout the semester. They only study to night before the exam. For them, their main concern is not to fail in the exam actually. Then again, there are some students who follows detection and recovery approach. They think passing in the exam is really very easy, even though they didn't study till midterm examination. After their midterm exam result, they will understand the importance of the study. For them, their main concern is they face the problem first and then try to recover it. And there are few students who don't bother to study. Here, their approach is ignoring the problem. Actually, they don't care about the examination. Those who are using prevention method, they only have to study. They cannot involve themselves in any other co-curricular activities. But those who want to avoid the situation, they will manage everything besides study. And those who like detection and recovery approach, after getting a start, they have to kill all other activities and restart their study. And those who are using fourth method actually, they are in different height. Education or graduation do not matter to them. They don't care it. So over here, all of them solve their own problems. But the question is, who did it or solve it better? The natures of problems are different from each other. So the main concern of the operating system is which approach should be taken considering the nature of the problem with minimum cost and time. In next session of the video, we are going to discuss how deadlock can be prevented, avoided and recovered after detection. Thank you very much.